Hello, everyone. I'm Oleg, and today we will talk about higher kind of data, and we will use Scala 3 as our main language. So, as we know, data is something to do with information, and usually to represent the data in programming languages, we use something that's called data structures. To define custom data structures in functional programming data languages, we use some basic constructions like building blocks. They are usually product types, sum types, function types, and some form of recursion in our types. At least it's said by some people in the community. Today, we will talk mainly about product types and their representations and problems and solutions for them. So in Scala, to represent products, we usually use case classes. So case class in the Scala is a named sequence of some types, and it you can call it something like a tagged tuple. So each field has some type and some name, and you probably all know it. So case classes, also known as records in other programming languages, are used. They actually very useful. They they're very helpful, and they can help you to write a type-safe code. So when you construct some record, all the types of each values that assigned to each of a field of your record are type checked. Also, when you can access any field in your record, and this again will be a typed expression. You have the correct type for this, and you can transform your records, modifying some fields with them, even constructing new values of the same record. And this again will have some type checking during. So records are actually super useful, and records like this could fill a lot of your domain model, and you will probably write a lot of code using this case classes. But one day you may probably receive some task that goes somewhere beyond the simple case class. For example, you need to store partially fields of your case class. For example, some user can fill some fields of your record this time, and then it want to resume to its process, and you must load some fields, only some portion of them from database, for example. So one way to do it is to give up on types and use some untyped things like map of string to any, and store all our data inside these maps. You can store this, you can store this, later you can combine them as just a normal map, and then you just write some functions that trying to transform your untyped map to your nice type record, and this is usually really painful, and this does not help your domain at all. Other solution could be creating of some twin case class. So you just define the same case class with same field names, where each of the types of your fields is wrapped in some option, for example. Then you need to write some some conversion routines for them, and some combination code. So if you're not familiar with Scala 3, it is how we define instances of some type classes in Scala 3. So this is mostly the same that have as implicit val, something of type, monoid, partial person. So next you need to define some utilitary instances for this case class, and you must remember that the whole point of this structure is for one task only. So you need to support the additional data type. You need to support its consistency with the original person type for the whole life of your project from this on. So there are another options. You can use reflection, for example. This is not really far away from the first example with map string to any. You can use shapeless, and this could be really painful, and this can even enlarge amount of care which you need to do during refactoring. So we must do another solution. Also, you can have another tasks for specific transformed versions of your record. You, for example, could need this thing like person variance when you have a list of possible variants for each field of your record, for example, for testing or for form pre-filling, for user to have some choices in the drop-down list. You can have some mutable person, for example, if your records will be safe in some shared memory. You may need to, I don't know, transform each field individually in some situations. You can probably need some record that represent some changes in each field individually, and some form of listener of these changes, when for each field you can assign an individual listener of exact field changes. And this is an example when we use contravariant type constructor that wrap in our original type. So there could be a lot of other specific single task types, and actually that could be really painful if you have the whole database filled with them and a lot of macros that transform in one to another. So the solution to this problem is known as higher kind data. It have been in the community, especially in the Haskell community, for some time. A couple of years ago, we have seen this beautiful paper about our higher kind types, and this is pretty simple trick. So instead of defining a lot of additional case classes, you just make your case class polymorphic, but polymorphic over some higher kinded type parameter. So this is why it is called higher kinded data. So this is type parameter is higher kinded, and you just wrap each of your field. You have just each of your fields wrapped inside this type parameter. So you keep types, precise types for each of your fields. Still, you have some polymorphism inside the structure. So it's a nice combination of typefulness and polymorphism over something. Then, having this definition, you can just redefine all your specific versions as just applications of your polymorphic case class to some specific type constructors. For example, original record will be just application of this person of to the identity type constructor. You can write it this way in the Scala 3. This is the special syntax to write higher kinded type constructor in place, higher kinded type aliases in place. And you can apply this to option to restore our discussed partial person. I can apply this to list to have the person where each field is wrapped into list. And you have other variations as well, when you can use a different different type constructors for each field. So it's really useful, but we have still the question how to work with it. So, okay, we defined a lot of data types. We don't need to define them manually. We keep them synchronized in our code base, but how to work with it? So from this point, we'll need a lot of implicit magic, or you can call it contextual magic in Scala 3. So let's start from the simplest routine. So let's think we need to fill every field of our data structure with its exact name. So we need to construct this structure that consists of field names for corresponding fields. So we can create a special type constructor for that. We call it name. We call names as a special type classy implicit instance of our person. And we can again create it by hand manually, but as well we can write a simple, very simple inline function. It's not even a macro. In Scala 3, it's actually a one-liner to produce a function that does exactly the same code. So it will fill all your records with constant strings. Each of them will represent the name of corresponding fields. This is the code in Scala 3 for that. Next, very simple, but super important and super efficient thing that we can do with our data types is fill our record with some evidences of some type class. For example, let's say we need an instance of show type class, get show type class that transforms some value to the string to show it in the console on another place. So we need to fill whole structure of show instance for each of our field types. So we can definitely create the code like that for each of our type classes, but also you can write a single line of code, again, function in Scala 3 that do exactly this for every type class that you can think about: show, source encoder, source decoder, EQ, or order, everything you can construct with this simple function that you need to write single time, or just take it from the library. We will talk later. So this is very simple things, but next we will talk about not that simple things. And we should talk about something called higher-kinded functors. But before we will talk about higher-kinded functors, let's talk about simple functors for beginning. So I hope everyone knows what functor is. It's a simple type class. When you have for your type constructor some property that you can use some function from its argument to another type, which can transform, which could transform your original value to the type constructor applied to the result type of this function. So you can apply this function inside your type, something like that. So let's start for simplified version of our person. Let's imagine if it were parameterized over a very simple, not higher-kinded, just a simple habitable type called R. So every field now is of type R. So now we can definitely define a functor for such a data structure. We can take our original person of A's and we can take our function and apply it to each field, and we can put the results of these applications into corresponding fields of the result. So this is, I hope this is a very simple code for you. We will put f of first name into the first name of the resulting person, f of last name and the resulting field into the last name of the resulting person, and so on. So this is a very simple, very simple transformation. We have another form of functors. For example, this little bit doomed abstractions called pure or pointed functor has a simple property that if you have a value of type A, you can lift this value into your type constructor. So fill everything inside the type constructor with this value, something like that. So again, if you have our simply parameterized person, we can just construct the resulting person when we put our given value to each field of our resultant data structure. So it will be just a structure, the field with the same value for every field. Very, very simple. Next, the super important and super cool abstractions that called apply or semigroupal functor. So semigroupal functor can combine two elements of the same functor using some functions from the types of arguments of these values. And it can combine them into the single value of our type constructors applied to the result type of our function. And again, with our simply parameterized data structure, we can do this as well. We can take from each of the structure each field correspondingly and apply our function to them and put the result in the corresponding field of the resulting data structure. So I hope this code is simple for you as well, because it's really important, and this catches the main thing that we can combine our case classes in a generic way. So the combination of this pointed functor and semigroupal functor is a well-known type class called applicative. We, of course, should add some laws on how this pure and map2 must interact, but this is actually a very well-known family of data types. Applicative functors actually, we don't need to write specific instance for it because we just wrote the code for each of required methods in the previous slides. So in the final, last but not least, how we should say, super cool and super important type class in functional programming called traverse or traversal functors. This is family of types, a family of actually containers. So this is a real container of some values, and you can traverse such containers with some effectful functions. So we have some function, and we could apply this function to each of element of our container. Then, using some applicative effect, arbitrary applicative effect, we can combine all the results for our fields and reconstruct our container inside this applicative functor. So this is really cool and really important. Some people likes it especially. And we can definitely write an instance of this functor for our data structure. So we need to do just what we ought to do. So we just apply this function for every field of a given data type. Then we combine all the results using map4 function that is just defined in terms of map2 for applicative. And then when we collected all the results inside our f, we can just apply a constructor of our person inside of our functor. So while we'll have a f of person of b as the result. So each of those elements was of type b, of course, and we have 4 of b values, and we will just combine them using the applicative effect, resulting in a person of b. So this is really important and really simple code to write. How you can, as you can guess, we don't need to write it manually, but we'll talk about this later. So now we will go to the higher-kinded versions of such functors. So higher-kinded versions of functors operates not on functions, but on something called transformations. It's not necessarily natural transformation, but usually in the language that have some magic property that called parametricity, all these functions are automatically natural. That's not really important information. What you need to know that we have this definition in our beloved cats library, and again we can write this type of transformation in terms of Scala 3 polymorphic function types. Scala 3 polymorphic function types are actually a little bit rough at the moment, but I hope they will get better during the time. So the idea of higher-kinded functors is popularized by this very nice library that's called Cat's tagless. It has some of the type classes, which we will talk later, and you will definitely need to check it out. So first abstraction is a functor K. Functor K is just a version of a normal functor, but it operates not on simple type constructors, but a type constructors that have higher-kinded parameters. So now we have this very higher-kinded type constructor that called U. It will represent our higher-kinded data type. And we say that we can transform each of f of arbitrary type into another type constructor applied to the same type, A. So we keep the internal types, but we change the type constructor. We switch the type constructor inside our data structure. So if we have our definition of person of, we will definitely write this instance for it. So higher candidate functor, as you can say, we take a normal function and we can just apply them to corresponding fields of our original given data structure. And if you can see, we will have the types checked and preserved inside those type constructors. So these constructions is well typed, and compiler will check that. Next thing is a higher candidate version of pointed functor again, but instead of just a value of type A, we can write a polymorphic values in Scala 3 yet, but so we have this nullary polymorphic function that will work like a factory for different, like an abstract factor or something like that, for different things inside the F-type constructor. And we say that given some higher candidate data type, we can actually fill the structure with values produced by this generator or factory, you call it, of the corresponding types. So in each of these lines, it will produce a value of different type, but they should be something like, for example, non-existent values for options, or empty lists, or something like that. So they should have a lot of common if we can write this function, actually, if we consider a pure function everywhere, of course. So the next really important abstractions is apply car. This is again a type class from cat-stagless library, and this allows us to combine two values applied to different type constructors, and we have a binary transformation here. So we can transform a pair of f and g applied to the same type to the third type constructor applied to the same type, and we can transform pair of different values using this transformation in this third value filled with the results of this transformation. So having our original person of definition, we can definitely define an instance for it. So we can write f of string and g of string as the first name of left and right structures, and transform it as an h of string of the result. Next, we do the same with last name. Next, we do the same with age fields, and next we'll do the same with lists of text. So this is very cool and extremely useful, and does actually with a very simple code that again we don't need to write by hand. So then we can have something called applicative K, that of course a higher candidate version of normal applicative, and again it's just a combination of Semigroupal functor and this pointed functor. So this higher candidate applicative functor is really cool, and this is helpful a lot. And finally, we can use this very cool thing that actually rarely can be defined for higher candidate traits, but can be easily defined for higher candidate data. This is higher kinded version of traverse. You need to check to read the definition very carefully. So originally we have our data structure applied to some type constructor, and then we transform this type constructor into the combination composition of two different type constructors. So outer one should be an applicative functor, and inner one could be an arbitrary data functor. So, and we, again, as in simple traverse, we guarantee that we will combine all the results of these G's elements, and we will leave H's inside our data structure. So the code that does it looks like exactly the same like a simple traverse from previous slides. We just apply our polymorphic transformation for each of our field, and each time we get here G of H of string, G of H of option of string, G of H of int, etc. Then we combine the G's, only the outer one of a structure, and we have a lot of H of string, H of something inside the single G, and we will combine them using our original constructor and the final combination. So next slide is not really important, but it could be helpful to know that we can derive an exact type class that describes higher kinded data. If you're familiar with tofu, you probably know what a higher kinded representable functors are. So if you combine this representable higher kinded functor with traversable higher kinded functor requirements for your data structures, that it looks like exact requirement for all this higher kinded data shape. And in the library that I will talk in the end of our session, we will have the code that can actually derive instances of these higher kinded type classes, and you will have all instances in this one. So it will be a traversable, an applicative, that means that it is also a functor, a pure, an apply, and so on and so on. So, okay, we defined a lot of, very complex things, but how to use it? So let's start from the code that automatically constructs a monoid for every higher kinded data that applied to option. So to define a monoid, we need to supply two methods. First is empty, which should construct a default value for our data structure, and this will be none, since our data is filled with options of something. The default value for them will be none. So empty is just a something that fills every field in our higher kinded data types with none. Second one is combined. So you have two elements of your data, higher kinded data types, which is a parameter here, and you can combine them in the single one. So we use this map to k method from the apply k data structure, and we just use the or else method. So we prefer the right one. If this is sum, the result will be the right one, and if the left one does not have sum on some position, then it will use the left one by the default. So this is a very simple monoid instance that we defined for all higher kinded data types at once. So you just need to write this code at once or import from some library. You don't need to write it for every higher kinded data structure. You can just use it. Next technique that you need to use with your higher-kinded data, I call it combine and traverse. So this is combination of map to k and traverse k methods of our data type. So, for example, what if you have your original data structure filled with options and you need to build some method? So it will be an extension method built that will result in either null. So either you have a data of an identity, just a simple data structure, original case class, or it will have non-empty list of strings filled with missing fields which are none. So it will check that every field is sum here, and if every field is actually non-empty, if it's filled with some value, we will construct the value. Otherwise, we will just provide the non-empty list of missing fields, and then the code that we need to write actually. So we combine our names. As you can remember from the initial slides, it's just a list of field names. We will combine that with our original structure, and using the syntax provided in the sketch, we just transform it to the right of the corresponding fields, or left of non-empty list of a single missing field that we have on this position. And then we just traverse all the results using this effect, either null, and we actually use a parallel traverse, a parallel version of this type, which just combine all errors, all missing fields into the single structure. And this is an example how we can use it. So first we can construct a whole structure of empty elements for our builder. Then we can fill some fields like first name and last name. So we create a copy filled with just 2 fields. Then we can create another copy when we fill another fields. And then we try to execute this routine that we described earlier, and we try to see as a result. So when we try to build from the empty builder, from an empty partial structure, as the result of our build attempt, we will just get the list of every field in our structure, because none field is here. So when we try to build this P1, we will have an error saying that we missing age and text here, and they are definitely missing. And the second one, we have as the opposite error that tell us that we are missing first and last name. And only this combination, again built with the syntax for monoid that is imported from the cats, we can finally successfully just build the resulting value. And actually this whole code is a library code, so we just get this all behavior for free. Second one, so next we will demonstrate that we can work with our structures with collections. So we will use the well-known trick where we use const types with the traverse to extract all the fields. If you're familiar with this trick, we have some special new type const, and we can actually ignore our data types, combining just this constant element. If you're not familiar, I'm afraid we don't have much more time to dive deeply into it. But this code allows us to actually extract all the values of our data structure into a single collection if we want it. Then you will need something called quantified constraints or quantified version of type classes. It's really useful. You can write them by hand and use technique in the library. On the last slide, I will show you. And we can just encode these higher-kinded versions of type classes. So higher-kinded quantified constructs means that for every type that have an instance of our type class, we have an instance of type class of that type wrapped inside these wrapped in this type constructor. So we have show for every identity of A if A is showable, option of every type is showable if A itself showable, and so on, so on. So we can write actually a generic code that will construct for us a show instance for every our higher kind of data type, for every possible f, if f itself have this higher kind of constraint. And this technique, you can look at this later, actually allows us to derive the instances in the automatic way instead of Magnolia, for example, in a very typeful and type-safe way, using just a normal code. So no macros here, no inline functions here. It's just a normal code that used some simple assumptions about your higher kind of type parameter and the general type class for your higher kind of data. So this is how you can derive show. You can require corresponding fields. You can import given this universal instance for your type constructor. You can extract, you can combine all the fields. You can actually show every field in your given data structure. So you have your higher kind of data field with strings. Now you just have a product prefix as well. Then you can have strings of pairs like this, again, using our combination technique, using map2. And then you just extract all the strings that we constructed on the previous step and just wrap them with the prefix of our data structure. And actually, this is not so hard. So you can, if you need just to define a new data structure, if you have enough of this generic code for your higher kind of data prepared, then using higher kind of data is really simple. You just write derive script here. You just derive some additional instances for it, and you just write code that use some other instances automatically, and this will work just fine. This is an example of running code using the snippets before. So to wrap it all, so higher kind of data is a way to give an infinite single use utilitary data shapes for your data type that can be in type safe way along with your original data structure and could be converted and combined in the good way. So also you can understand that record-like collections, like indexed collections that index both with types and names of your fields. And you can actually have a nice type class instant derivation for different higher kind of data types without any funny macros using just very small and simple code snippets that we showed before. So we didn't cover something else like product besides product. So if you have some recursion of function types inside, you can just just put IDs for them, and you can just use them using the same technique inside your higher-kinded record for the null. And you, if you have some sum types, especially some sum types, enumeration, algebraic data types with recursion, it's actually much harder than thing we discussed just before. And actually, we will think about much more complex ways to do this, but in later talks and blog posts.